Okay, so I think we've got a lot of people, so I'm just going to start. So, hello everyone, welcome to our Tech Talk today. My name is Sophia, and I'm part of FTC Team 21229 Quality Control. We are an FTC team that has qualified for the World Championships for the past 2 years, and we were the 2023 World Champions. And today we have the honor of co-hosting this event with Husky Robotics from the University of Washington. So, they are a robotics team that builds Mars rovers to compete in the International Rover Challenge Series, and they have won second place for the past 3 years at the Canadian International Rover Challenge. So today they'll be giving us a talk on control systems, and we hope you enjoy. So I'll hand it off to Husky Robotics now.
Yeah, awesome. Thank you for that introduction. Hello, everyone. Again, I'm from Husky Robotics, and I'm here with two other Husky Robotics members today. My name's Amelia, and on the team, I'm the systems lead. So I oversee all of the operations on the electronic side of things and the software side of things. And then I'll let Michael and Andy introduce themselves as well.
Yeah, hi, I'm Michael. On the team, I'm the firmware lead. So I do a lot of the embedded like coding, like dealing like making sure that the boards are behaving the right way. Um, yeah.
Hi guys, I'm Andy. I'm the hardware lead. Basically, my job is to make all the hardware parts. We do all the wiring on the rover, and then we make customized printed circuit boards to make the electricity work. And then um and yeah, that's my team.
Yeah, and we can totally talk about kind of more of like the specifics that we do as a club, like later on after this presentation, if anyone's interested. And then we'll also have like more tech talks and like we'll set more up with Sophia. So we can talk about more things in the future as well, revolving our team. But today we're going to be talking about like an essential topic in sorry, an essential concept for robotics, which is control system. And I just want to give a little introduction to what a control system actually is. So Michael can switch to the next slide. So, a control system is a mechanism that manages commands or regulates the behavior of other devices or systems. In like the most simple terms, it's like a brain that helps keep everything functioning smoothly. And control systems can be divided into two types. The first being open loop, and then the second being closed loop control systems. And then I'll talk a little bit about what an open loop system and a closed loop system is. An open loop system is a system that operates without any feedback mechanism. It simply follows commands given without like considering the actual outcome. For instance, if you set a motor to run at a certain speed without any way of knowing whether it reaches that speed, you're using an open loop control system, if that makes sense. And a common example of an open loop control system is a washing machine because once you set the time in the cycle, it just like completes that whole process without any adjustment based on how clean the clothes are or anything like that. And then these types of systems are generally simpler and cheaper, but are less accurate because they can't really correct any errors that occur in a system's operation. And then on the other hand of things, like I was saying, we have a closed loop system as well. And this is more common when it comes to just controls and robotic devices in general, because it like incorporates feedback that we can use to adjust its actions in real time. And this means that the system is constantly like monitoring its outputs and makes sure that there's necessary changes to like reach the desired results that we want. For example, in robotics, if we want a motor to like remain at a specific speed, we would use sensors like encoders to continuously measure the speed and make adjustments if the actual speed like deviates from our targeted speed. And this is called feedback control. You can kind of see like a quick simple diagram of that on like the slide, and like that feedback control loop is what makes a system closed and makes closed loop systems more reliable and accurate. Um, closed use closed loop systems are used in scenarios where precision is really crucial, such as maintaining a robot's position or keeping a motor running at a constant speed, regardless of any external factors like changes in load or power supply. So, in summary, the key differences between open and closed loop systems is whether or not there's feedback being used, and then an open loop system is just straightforward, but it lacks accuracy, while closed loop systems use continuous feedback to ensure precision and reliability. So that was just like a quick introduction to just the most basic concepts of controls. So before I move on to the next slide, does anyone have any questions? I'm not sure the best way to see if people have questions either, but I think there's like reaction settings. So if anyone has a question at any point during the presentation, you can just put a reaction on and then we'll know that you guys have a question for us. But if not, we can move on to the next slide. So now I just kind of want to get into like FTC specific applications of control systems. And like three of the most important things that I thought I wanted to like talk about with you guys today was using like PID controllers for motor control, and then also the use of gyroscopes and IMUs for maintaining direction, as well as like just talking about automation in general. Like after looking over what like your guys' what FTC teams do in general, it seems like these concepts come up a lot, and just going over like quality controls like repository on GitHub, it just like we could see a lot of these concepts being used. So I'm just going to go over these things a little more in depth. So yeah, you can go to the next slide. So the first thing I wanted to talk about was, again, PID controllers and how they're used for motor control. So this is like one of the most common control methods, it seems, in FTC robotics. And but I just want to talk about what exactly a PID controller actually it is. So PID stands for proportional, integral, and derivative. And these are three mathematical functions that work together to like minimize the difference between a desired set point, such as a target speed or position for a motor, versus like the actual value being measured. So I'm just gonna go into like all three of the parts of a PID controller. The first being the proportional part, the P term, which corrects the error in the proportion to its size. And this just means that the larger the error, the larger the correction. And then, for example, if your robot is far away from a desired position, the proportional control will apply like a strong correction to bring it closer. However, just like having this part of a controller, just the proportional control alone, can sometimes cause a system to like oscillate or overshoot the target because it does not account for like the momentum that like a system is building up while correcting the error. And we're gonna get into this a little more later when we do our PID tuner activity. So we'll explain like oscillations and overshoot a little bit more later. And then, but for now, I'll move on to the next part of a PID controller, which is like the integral term. And the integral term accounts for the accumulation of past errors. So it integrates the error over time, meaning it looks at the a total amount of error that has occurred and works to eliminate any like residual steady state error. Again, we'll talk about that a little bit more later, but this is like really useful if there's a small but persistent error that the proportional term alone can't correct. For example, if your robot is consistently stopping just short of the desired position, the integral term will like gradually increase the control effort to push it the rest of the way, if that makes sense. And then the derivative term predicts the future errors based on like the current rate of change. Essentially, it measures how quickly the error is changing and applies corrections to prevent overshooting and oscillations. So the derivative term acts as like a damping force or like smoothing out the control response and making the system more stable. Like, for instance, if the robot is approaching a target too quickly, the derivative control can reduce the motor output to slow it down and prevent overshoot, like I was talking a little bit about earlier. And just like by combining all three of these components, you get your PID controller. And this is what like most control systems use to provide precise and stable control. And in FTC, you might want to use a PID controller to control a robot arm to lift to a specific height or ensure that your robot drives straight even when the battery voltage or the surface is uneven. And like a key advantage of having PID controllers is it gives you the ability to create smooth and precise movements, which is crucial for tasks like placing game elements accurately during your matches or just having precise movements in general. And proper like tuning of PID values is essential for like having an optimal performing system. And this process often involves a lot of trial and error. So it's just like trying to find the right balance between responsiveness and stability. And you'll be able to see this again in real time when we do our PID tuning activity a little bit later. But yeah, that's just a quick introduction to PID. But does anyone have any questions about that? I know that was kind of just a lot of information. So it's okay. No one has any questions for now. But awesome. Yeah, if no one has any questions, we'll move on to the next part, which was using gyroscopes and do you say gyroscopes? Is that how it's pronounced? I don't know why I'm thinking of like the food euros. So I want to say like euroscopes, but anyways, but yeah, so the next thing I'll talk about is gyroscopes and IMUs for maintaining direction. So again, like we already talked about a bunch of corrections, so now we want to talk about kind of like how to keep your robot heading in the right direction. So, and then gyroscopes and IMUs, which stands for inertial measurement units, are very like crucial in maintaining stability and orientation in FTC robots. So these sensors are critical for ensuring that your robot can navigate accurately, especially during like the autonomous phase when there's no driver input. And just to like tell you guys what a gyroscope and IMU are, a gyroscope measures rotational velocity, which is essentially like how fast the robot is turning around an axis. And by integrating this rotational velocity over time, the gyroscope can provide an estimate of the robot's orientation. This is particularly useful for maintaining a straight path or executing precise turns. For example, if your robot starts to veer off course, the gyroscope can detect this deviation and like you can use your control like input for your whatever controller you're using to like make a corrective action to bring the robot back on track. And then like an IMU is an even more powerful device because it combines multiple types of sensors, like including a gyroscope too, actually, and then also accelerometers, and then sometimes even magnetometers as well. And then the accelerometer, like part of the IMU, measures the linear acceleration along different axes, which can be useful to determine changes in velocity and position. And then the magnetometer, if it's included, measures the magnetic field and can help determine the robot's absolute heading relative to the Earth's magnetic field. And by combining all of this data and IMU provides a really like comprehensive picture of the robot's motion in general, and then including both the orientation and acceleration of your robot. So yeah, this allows for like a very accurate control, like especially with like complex movements that require both rotational and linear adjustments, which seems like your guys' applications. So yeah, and just like generally in FDC, like all of these devices like are just used to help your robot maintain a straight path by correcting any deviations. Like this is especially useful during autonomous mode when you want to drive in a straight line, even if the field surface is uneven or if the wheels slip. They can also enable very precise turning, like turning exactly 90 degrees to if you want to align with a game element. And then just one important thing to keep in mind with all of these sensing devices or just for gyroscopes like specifically is like you have to like l- calibrate these devices properly to make sure there's no drift over time, which could cause like inaccurate readings of the devices. And then drift is just like a gradual deviation that occurs due to sensor errors like accumulating, which is why recalibration is really necessary if you're using these devices. And kind of like what I mentioned earlier, like pairing these types of sensors with a PID controller can further enhance the like stability and precision of your robot. But yeah, that's about it for like these sensing components. Does anyone have any questions about this? And if not, I'll move on to the last topic I wanted to talk about. Um, so yeah, Michael, oh, thank you for switching the slide. Which is like just talking about automating sequences for autonomous tasks. So first I can just discuss like automation, automation in general. So yeah, in FTC, I don't know why I can't say that word. Automa Wait, automation? Okay, automation. Sorry, but now I got it. Automation in FTC like means programming your robot to perform a series of actions without any human input at all during like the autonomous phase of the match. And this requires careful planning and precise control that like to make sure you're ensuring every action is executed as intended. And control systems play a key role in this by allowing the robot to use sensors and feedback loops to make sure like actions are carried out accurately. For example, like imagine you're programming the robot to move to a specific zone, pick up a game piece and deliver it to like your target. And to do this effectively, the robot must use various sensors to gather information about its environment and adjust its actions accordingly. So I know I already talked gyroscopes and IMUs, but another type of sensing device is encoders, and those are used to like measure precise distances traveled, and these devices are attached to the robot's wheels or motors and provide feedback on the number of rotations, allowing the robot to calculate how far it has moved. And this is really crucial for ensuring that the robot stops at a correct location if you're using it for like automating tasks and stuff. And we use encoders all over like our robot. Like on our rover, we have like a 6 degree of freedom arm and then a drive base. And on almost every motor, we have some kind of feedback device like this so that we're able to like control it effectively. And then another thing I wanted to talk about was limit switches and distance sensors or even color sensors. And these can be used to control different manipulators. Like, for example, if a limit switch can detect when a robot arm has reached the end of its range of motion, and that can prevent any damage by stopping the motor. And then distance sensors can help determine how close the robot is to an object, which is useful for tasks like picking up a game piece or anything like that. And then these sensors, like paired with any closed loop control, ensure that each task is completed consistently. And then, like, the robot uses this feedback from sensors to adjust its movements in real time, making sure that it reaches its desired position and performs the correct action. This level of automation is what allows, like, robots to perform complex sequences during, like, competitions similar to your guys's and our own competitions. Like, however, like doing anything with automation doesn't come without like challenges. Like one key challenge like that you have to think about is sequencing and like sequence timing in general, which means just making sure that each action is completed before the next one begins and ensuring that actions don't overlap or interfere with each other. For instance, if the robot tries to move while its arm is still extended, it could cause instability or even damage. So to address this, it's like important to very carefully plan out the sequencing of actions and include things like delays or different conditions in your like code interface to ensure that each step is completed before moving on to the next. And then another important thing is like error recovery in a dynamic environment like a like robot game match. Like there could be unexpected obstacles or misalignments that can occur. And for example, the robot might encounter an object that you weren't really anticipating to be there, or it might not pick up like a game piece correctly, even if it was supposed to. so to handle these situations, it's a good idea to like implement a lot of checks or like logic checks in your coding, like that'll allow the robot to detect when something has gone wrong and take a corrective action. So just continually checking that you're operating like how you want to operate is really important. And this could involve retrying a particular action or adjusting the robot's position based on like whatever unpredictable condition happened. But yeah, and that pretty much wraps up the main concepts that I wanted to talk about for the control systems in general. Again, like I just want to emphasize that like the control systems are at the heart of robotics and they just like enable you to have an effective robot and do effective controls. So hopefully that was like a good introduction to all of these topics. And now we kind of wanted to move into like actual like applications of like what this would look like. And we're basing like this off of like looking at the GitHub repository for quality controls code and just looking at some of what you guys are doing for controls. And we just wanted to like kind of do like a live code review, just talking about your guys' system, like and what you have in place so far. And hopefully it can be useful for everyone here today. But yeah, so Michael's gonna take over that part. But thank you. And then before we move into that, like let me know if anyone has any questions. But yeah, if not, Michael, I'll let you take it over from here. Thank you.
Okay, yeah, so I've just been asked to, I guess, like Amelia said, review the code. Which actually, let me change my screen share, real quick. Okay, okay, can you see my, like, entire screen? Okay, so I guess to start, okay, I kind of, like, am presenting this way, I guess, but to start with the motor move command, I'd say most of my feedback is or functionality seems good. Most of my feedback would be style, and like code readability and like best practices. So to start, just looking at these fields, since we're using Java, best object-oriented programming practices, you should probably declare these as private. Just like because usually we want to limit the visibility of variables in classes if you're not using them elsewhere. Um, this function, I saw it could be used, it was the same like kind of equation is used here and here and here. Um, so maybe you could utilize this function acceleration distance more. Um, and that would like help with readability. And if you introduced like a parameter for time, then you could like this function could be more flexible. Um, I guess more style stuff is that for like repeated calls to system, current time millis, and also math.signum. Usually we want to avoid calling things repeatedly, so maybe you could store them the values in a variable and then use those variables so that it's not processing the same thing multiple times. Um, let's see. Okay, so for PID, which is what we were talking about previously, what do I say here? Okay, I just had a couple questions about the usage. So for PIDs, like it can be used to set like targets for like I guess precise control of multiple things. So here I was a bit confused on like what exact sort of um value or like thing that you're controlling. So get current position to me seems like the motor angle. Whereas for like the value S, it seemed like the actual physical distance of the robot. Um so that is one thing that maybe might be good to get more clarity on. Um, because here I looked at this function, it seems like S is the set point. Um, so if you're looking to set like the physical distance, that would be good. But if you're looking to set the motor angle, then that might be like a different value that you need. So that I was might be good to look at. But of course, like the idea behind it is like you guys are more familiar with. So maybe like it depends on what you're actually doing. Um, Also for the feed forward offset, I guess, I was wondering why not use the PIDF function or controller, which seems to integrate the feed forward. I mean, maybe it's a decision that you guys made or that y'all made. I was just curious why. Um, let's see. Also for the end function, I was curious as to why this target position was being set for the position coefficient or the proportional, and then this position coefficient was being set to zero afterwards. Um, it seems like they're setting the same thing. So I was curious as to why like having them separate was the case as well. Um, but for PID improvements here, I would say like like once the PID is like you have all the parameters set, maybe a thing that you could add to this file is if you wanted to sort of automatically update parameters if they're not if the PID controller is not being maybe like performing optimally. So maybe if you get some feedback about like, oh, the final position is has like this certain offset, you could automate one of the parameters to deal with that error or like automatically update it and then like change the PID controller that you're using like programmatically. Um yeah, so that was a lot. Are there any questions about this? I have some more code style feedback about this function, but if there are no questions, I can move on.
Wait, so like by automating the like PID, would you mean like so we get kind of feedback from the robot and then like what's happening and then we kind of have a variable that just like adjusts to it and then we like run it again. Can you kind of
Right.
explain what you mean by
Yeah, because yeah, exactly, because we were looking at these parameters, these coefficients, they adjust for like different things. So if you say, yeah, you get your feedback, and there's a certain area that your controller is like not sufficiently accounting for, then you can update that maybe and then like update the controller.
I see. Okay.
Okay, servo move command. This one I didn't have too much to say. Um, I mean, it looks pretty good. I just had a couple of nitpicks. So like this sort of code is repeated, so it might be good to wrap that in a function. And then this is very nitpicky. Um, but like maybe for readability, you could um change this to like store this as a total time variable, or like store this time MS, just so that it's like easier to understand what's going on. But for the control stuff, I looked at the FTC library, didn't have too much on feedback about controllers, but I guess the same sort of control theory can apply if you're able to get feedback. So you could still implement a controller, and make sure that it's getting to like the right position. But again, if the libraries that you use don't have any feedback for that, that might be a bit difficult. Um, okay. Motor tuner Java. Okay. This one I did have comments about. I guess, feedback more so about just repeated code. Um, which let's see. Yeah, so these two parts seem nearly identical except for this sort of input, which seems to just be the target position. So maybe you could put this in a function, and have like a get target position in the motor command. And then that way you could just wrap this in a function and then it's like more concise. Um, I guess with that too, these two parts seem to be like pretty similar, with the only difference being again the target position. So if you could wrap that behavior in a function as well, that would be good. And then like I like what you did with the pause function. So just more of that, more of like um just like making things more putting things into functions and making it more readable would be helpful. Um so like here this is pretty similar to here. So again that's maybe another place that you could um improve. Oh, oops, that's the wrong thing. Okay. Um yeah. Are there any questions about what I've said so far?
No, I don't think so. Like, thank you so much for the feedback, though.
Okay. Yeah, and again it's like it's your code. So it whatever you want to do is up to you really, but these are just like some uh common practices that I've seen in like Java specifically. Okay. Last one, intake, outtake. So for I guess because I've been talking about code style a lot, there is not a lot that I would add for this. I would just say like the numbers that you use might be better to like usually we want to like even in the code that we use try to avoid magic numbers. So like just numbers that show up in the code. Usually we try to define them as constants, because that will I guess do two things. If you want to change like one value, you don't have to change it multiple times, you just have to change the value that you store. And then also giving it a descriptive name will help with readability. But I think one thing for these, like the intake outtake commands, um, so there are things called state machines that sort of like they sort of separate different behaviors into different states. Um, and so based on some input or based on like the current state of the machine, like the state of the robot will go into another state and that state will have different behaviors. This might be something to look into if you're interested. It'll be helpful for automation. It's like a more organized way of separating behaviors out. So you have like a one state that has certain behaviors, and then based on the current state or some input, you might go into another state that has another set of behaviors, and that can help with sort of automating things, and being more organized in that automation. So that might be something that you can add here, and might be something to look into too. Um, yeah, any questions about that?
Nope, I think it sounds good. Yeah.
Okay.
We will
All
also
right.
probably ask you if we have more questions later on, I think, as we're trying to implement some things.
Oh yeah, for sure. Okay. So that is about it for me.
Okay. Awesome. Thank you, Michael, for talking about all of that. And again, yeah, that was just us kind of just picking out like random code files that you had in your repo, just seeing like which ones we thought like applied to like the applied to most to what we're talking about today. So yeah, if you guys have any more questions about implementation stuff like later on when you're trying to like do more stuff, let us know for sure. But yeah, now I'm gonna pass it over to Andy, and he's just gonna walk you through like kind of like what an actual PID like simulator like looks like, and just like more considerations when doing tuning like this. So I'll pass it over to him.
Um, Hi again. My name is Andy, and then I'm gonna show you how to actually tune the PID. And I'm gonna um put a link in the chat. So this link is what we just kind of we just kind of found like an online PID tuner, and it should look pretty straightforward. And I'm gonna share my screen real quick. That's okay. Okay, awesome. Can you all see it? Okay, awesome. So we're gonna learn about how PID controllers work, and we're gonna do like this is like an interactive simulator to get some hands-on experience with them, and let's dive in. So, to just review the PID for the PID term, the P stands for proportional, I is integral, and D is derivative, and each of these components affect the system differently. P deals with the present, I with the past, and D with the future. And together they help control system they help to control the systems in a stable manner. Um, to make an analogy, you can think of the PID controller like as like driving a car, and then proportional, which is P term, it's like how hard you press the gas pedal based on how far you are from the target speed, because you change you press the no you press the pedals to change your car speed. Um, and the integral term what takes in how long you've been off the speed, and then the derivative in term is like how quickly you're approaching your target speed. So it's like that. Yeah. And then some real world examples. And basically PID's controllers are like the fundamental of the control system. They're used everywhere. They help keep like I mentioned, the car's cruise control steady, or like to stabilize the drone, and then or other industrial processes like keeping temperature in the reactor stable. And then we're gonna use a simulator today to visualize how that works. So before that, I want to point out, for P, there's also other controllers such as the PI controller and the PD controller, and then today, well, and then the PID controller is more, I'll say more robust than the other two, but the other two controllers are also used for different functions. If you want like a temperature, like what I mentioned, um you want to like control the temperature, or like just takes in temperature data, it um the fast response, when the fast response isn't that crucial, you can use a PI controller, because it will help um stabilizes, and then it won't get any overshoot at the end. But it reacts a lot slower than a PID controller. Why for a faster application, like your robot arm or your drone, where it needs to like react immediately when you like press a button, like when you uh use your controller to control your robot, it wants to react immediately. You will use a PID controller or a PD controller. And then the the advantage of the PD controller is that um it will it was it will react to the sudden changes pretty fast, and it will go back to its destined state. And then why and then sometimes the PD controller would be more beneficial than PID, um because like PID has 3 parameters. It's a little bit harder to tune, but PD has 2. So today I'm gonna show you. So on this interface, we have the red, blue, and green. And the red one means the control input. What that means is what your current position of the robot arm or whatever it is. Let's use robot arm as an example today. And the set point is what you want the robot arm to be. And then the output is what the control system should react to based on your input and set point. So if the set point is lower than input, then the output needs to like go higher to make up for it. So and I'll have the set point to negative 58, right? And then let's see. I want to change. I want to move the robot arm, let's say, to -4. And I have default settings, KP, KI, and KD. So PID. So as you can see here, there's like a lot of overshoots. It's like a waveform, and it's like it settles pretty slowly. And then can anyone take a guess of what happened if I increase the KP? You can put it in the chat too. I'll give you a few seconds to I'll give you a bit to think about it. Overshoot more. Any other guesses? More violent. Okay. More violent. Okay. Now it's time that we find out. Okay. So let's move the robot arm again. Sudden change. Now we increase it to, say, 3. What do you think happens here? What's your observation here? Okay, I can increase a little more. Or let's go back to the original and increase. Let's see. Let's see again. Let's increase a little more. So as you can see, when you increase the proportional gain, the system would react a little like you said, more violently, because and then if I go back to a lower value, it will it's like a weaker controller, so it's like more, it's like less convincing. I don't know what's the best term to describe it. But if you like again, when you increase the proportional gain, it it increase the proportional value so that it responds faster to the change in system. So it has a shorter time to settle down. But okay, now we have increased the proportional gain. It uses less time to settle down, but there are still overshoots. So let's say you only have the p-value for your robot arm. If you purely increase the p-value, your robot arm is gonna move up and down, and then do that, which is not optimal, but better than a small value. But can you guys take a guess of what happened if I increase the I value? You can put it in the chat. Okay, I guess it's a little hard to guess, but let's see. Let's see what happens here. Oh, oh, oh. Don't do that. Okay, don't want to do that. Okay, there you go. Okay, let's not take it a little bit. Okay, as you can see, as you can kind of see here, um, when I increase the I value, it makes the function a lot more smoothly, a lot more smooth than just having the p value. Um, and this is what integral does to us. It smooths out the signal when there's a change. Um, um, and then the next thing is the derivative gain. You can also take a few seconds to think to kind of get to try to guess what this is gonna do to your system. Like what if I increase this value here? Like this is without the derivative change. The derivative gain looks like that. Damping oscillation. Hmm. Any other guesses? Again, it's this. Also, keep in mind this is a relatively slow response. How do you make it better? And yes, you increase the. How do you make it better? You increase the D value. Let's make it 0.43. And let's see what happens when I move it. Do a sudden change. Oh, that's not good. Okay. Oh, nice. It only oscillate 3 times. Shut it down. So like this derivative gain helps the system to respond to the error faster, to like settle the error faster. So, and sometimes when you're the reason I mentioned PD and PID control is that sometimes your robot is really advanced from the hardware perspective. Like on the hardware side is pretty advanced as encoders and then all kind of feedback. You sometimes don't need the I term. Like sometimes if you increase the I term to like a relatively big value, it will do this. The robot will like explode. Not like explode, but like the movement will be like very unstable because it will like overshoot. It will think that needs to move more, while in reality is overdoing it. That's why overshoots happens. And then on the other hand, uh oh uh Nishant, do you have a question? Yeah.
Yeah, I was wondering, how do you deal with transport delay in the PID controller?
Transport delay. Uh, what do you mean by that?
Like when the sensor reading is like delayed from the actual motion.
Sensor readings delayed from the actual motion. It's a good question. It's delayed. Not sure if that's a problem that PID can handle. Um, Amelia, do you have like you have an idea for that?
I I want to say I'm gonna look into it more while you're like finishing explaining everything, Andy, and we'll get
Yeah.
back to you at like the end of the presentation. Because I was just talking to someone about this, and I want to like look at my notes from this to answer your question. But yeah, we'll get back to you if that's okay.
All right, thanks. I was also wondering, how do you deal with like lower sample rates?
Over sample rates. I like these questions. Okay. Lower sample rate. Um, I guess. Hmm.
Are you talking about with just like motor feedback specifically? Like you're like sampling, like you've had problems with like the sampling time being like too little, and then like, oh, your controller can't be fast enough to correct things. Is that what you're asking about?
Yeah, like we tend to have more oscillations when our sample rates get worse.
Mm, yeah, and then is it just because of like your feedback systems like can't handle like giving you like better feedback or like faster rates?
Um, maybe the error just builds up more during like in between samples. I'm not really sure.
Yeah, we'll get back to you on that as well. That's a really good question. But yeah, we'll get back at the to you at the end of this presentation. And then since we don't have a lot of time left either, like for some reason if we don't get to it, like we'll be sure to like send out like these slides after and then also like a document answering those questions as well.
Um, I would say for lower for that question specifically, you could try to like find some ways to like filter the input signal, and then like you can also like adjust these gains to make the system react a little slower because you have like less a little bit less precise like I mean like lower sample rate that makes like the input like maybe less precise, um and then you wouldn't want like a more violent feedback because if it's like imprecise, a small error can cause like a huge issue. uh so yeah, just like um maybe like decrease the gain, so like the whole thing will react a little slower. Like I talked about the temperature the temperature example, um but but apparently this is a robot. um yeah, I think that should be the direction I'll go for. um
All
yeah,
right. Yeah.
yeah, no problem. And then another thing uh, I wanted to talk about is like the overshoot. Like when you also like when you increase the integral gain, as you can see, it'll overshoot. Sometimes overshoot, but you can set a cap here to like um to like limit the overshoot by putting a cap on the integral value. And also there's like a feed forward equation. So feed forward, I don't think they mentioned this, but feed forward means like the error, like the input error, uh, and then you can like return like a let's say three. Um, wait, that's a little too small, right? Let's see. Okay, I don't think this is working. Okay, anyways, uh, feed forward just means like there's your 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 robot system is working normally, and suddenly there's like an error that inputs maybe like maybe it's like an obstacle or something. That's what the forward does. And you can tune your system in a way that it can take care of these feed forward errors like efficiently. Um, and now what you want to do, let's see. Um, Amelia, how's the time looking?
We have 5 minutes left, so maybe
Oh, 5 minutes.
just
Yeah.
wrap it up in the next three
Okay.
minutes, and then we'll like leave 2 minutes for questions.
Okay. Um, let's see. So, um, let's see what should do. Okay. Um, so I want you guys to like, I guess type in the chat of like what PID values you want to try, and then we can show them here. If you guys want to do that. like what KP is, what KI is, and KD, and then currently there's like a range for them. So like this is from 0 to 5, and then we have 0 to 20 for the KI value. Oh, okay, that's not good. Yeah, you see what I mean? Like when you have to be careful with like the parameters because wait, if you don't tune it properly, it will overshoot like this, and which is pretty bad for your system. Uh, um, and then this one is oh no, is 0 to 5 also, and also for like the KD term, uh, when you uh when you increase it too much, when it's way too big, it would even at the steady state level, it will also oscillates a lot. Let's see. Okay, no guesses. I think we should wrap up here.
Yeah,
And that, yeah, and
yeah.
yeah, this is the link I posted in the chat, and you can just kind of play around with it, um, and then yeah, that's PID for you.
Yeah, yeah, it's a pretty cool application. Again, Andy sent the link so you guys can mess around with it. But yeah, and it's like it's definitely like easier to mess with it on your own too. But hopefully that gave you like a good introduction to it and just like hopefully this whole presentation in general was like useful for you guys like at least at a surface level to learn about these concepts. But yeah, I know we only have a few minutes left, so if there's any more questions, like I think that's all we have, or if like Sophia, you had anything else you wanted to say.